Welcome to the experiment on redox reactions and in particular on redox potential and Nernst equation. In the first step, we prepare all the solutions we need for the experiment, and here we want to show you how we prepare 1 mole of sodium chloride. So what you see here, Claudia uses a beaker to weigh out the sodium chloride. So she puts the beaker onto the balance, makes sure that she takes the tara of it, and then weighs out the amount of sodium chlorine which she calculated before. She adds that, writes down the amount, and then starts to transfer the sodium chlorine from the beaker into the flask, okay, the volumetric flask. So she uses here a funnel, and step by step she dissolves the sodium chlorine and transfers it from the beaker into the volumetric flask. Okay. Here, okay, all gets very, very carefully transferred so that we don't lose any of the material. Now everything is in the funnel, and then she uses squirting bottle to transfer from the funnel and into the volumetric flask. Okay, so carefully she does it, adds it, and once everything is washed down from the funnel, then she fills it up to the line, to the mark, and at the end you do use the squirting bottle again to be very, very exact. Then you see the meniscus hits the line. Then our 1 molar sodium chlorine solution is ready, and now we mix it very well. Okay, we can do that by shaking. We can do that into put it into ultrasonic, whatever helps to dissolve it. And once it's well dissolved and mixed, then we label it with a marker. Okay, here 1 molar of sodium chlorine solution. We want to look at the movement of electrons in solutions and in solid materials. This experiment will be just qualitatively, so we won't do any measurements or any quantification, but key to these experiments are here the multimeter, where we can measure currents and potentials. Okay, and in first instance we want to just check the batteries if they are really alive, if they are not flat, and we want to check if they have the potentials they should have. So here we first connect a 9-volt battery to the multimeter, and you see, depending on how you connect the plus and the minus to the wires, you get, of course, a positive or a negative reading, but the potential is 9 volts. Okay, so this battery seems to work fine. Happy with that one. Now we want to test the small ones. They should be 1.5 volts. Again, we connect the wires to the poles, the plus pole and the minus pole. And again, we get the right reading, so we are confident that our batteries work and we can use them for our experiments. The first experiment, we want to look at the conductivity of materials. So we connect the wires to the battery so they give it the power we need, and we connect it to the bulb, and of course the bulb will shine because the current is directly going through the bulb. Now we put in between the pathway, we put different materials. Look what's happening. So the first material is a metal rod, and indeed the light is going. Okay, so the current is going through the metal rod. When we use a rubber, then nothing happens. So the rubber acts as an isolator. And then you see still a plastic strip and a carbon
pencil, okay, and the plastic strip, as you see, a little bit tricky. There's no light going through, but when we go through the carbon, then there's light going, current going through, and we see the light. Good. Now we want to look at solution, and in that case, we have two copper electrodes, which we put into water, and you see we get no current running. Now we clean it and put it into a solution which has sodium chlorine in it, so the 1 mole of sodium chlorine, which we just prepared before in the previous step. And now we have, of course, an electrolyte, so we have sodium and chlorine in the solution, and now the electrons can flow, and indeed we are measuring now the current. In the next steps, we are preparing the electrode wires which we need for our galvanic cell, and we need to prepare a salt bridge. First, electronic wires, we have to clean them. We use for that sandpaper to get any oxidation of the surface, that we get rid of that. And then we prepare the salt bridge, which is needed to enable the electrons to go from one half cell to the other half cell. So that purpose, we add the electrolyte into a plastic tube, okay, which acts as salt bridge. So on one side we first put the cotton, okay. Then we take our electrolyte solution. Here in that case we use potassium sodium chloride. So we put it, decant it first in a beaker, so that we can pipette easy. Now we take the pipette, slowly pipe it up, okay, so be careful, not too quick, and now fill the tube, okay, so that it's filled all the way to the cotton. It's a little bit tricky, so you need a little bit of patience here. Okay, that was probably a bit too fast that we took up the solution. So you see we had bubbles in the pipette, but it doesn't matter so much because we are not quantitative in that case. Okay, so we have now the sodium chlorine in, and now we have to plug the other end. Take again the wool and place it in our solution. Okay, here we go.
Now we move to step 4 and assemble a Daniell cell. To this end, we have to construct our two half cells. In that case, we have a zinc and a copper half cell. Each half cell has the metal rod and the corresponding salt solution. So zinc, it's zinc sulfate solution, copper sulfate solution. We have them both at 1 mole. Okay, that are the definitions. And in that case, we connect the electrodes to the multimeter. We add the salt bridge, which we just built, and then we can read the potential of our Daniell cell consisting of the zinc and copper electrode. That's the next step. We exchange one of the half cells, in that case the copper, with the iron. Okay, so again we use the half cell where we have a 1 molar iron sulfate solution, which we use a iron electrode, okay, which we clean, which makes sure that they it's not oxidized on the surface, and then again we connect them to the multimeter and measure the cell potential. And remember, the cell potential, of course, is the difference between the half cell potentials between the zinc sulfate and on one side, and the other half potential, which is from iron sulfate redox reaction. Okay, and then we know the cell potential and compare it with the theoretical calculations.
So, in the next experiment, we want to test and validate the Nernst equation. To this end, we construct a cell with two half cells which have silver nitrate as an electrolyte and silver wire as an electrode. So first, both cells have the same concentration, in that case 0.01 molar. We put them into the stand so that they don't move around, so it's easier to fix the cables and it's not falling or dropping. Okay. So we connect the wires. And at the moment, of course, the electrons can't move around, so we don't measure the in potential. So you see on the meter that we get 0. And now we add the bridge. We've already prepared them, so that's the one which we did before. We add the bridge, now the electrons can move. But of course, because the concentrations on both sides is the same, potential, the cell potential is 0 as well. So the same like without bridge, basically. Good. And now we exchange one of the half cells. We take the half cell on the left in that case, which we exchange with a solution which is 10 times less. Okay, so already prepared that, so that has a sodium chlorine solution of 0.001. Sorry, silver nitrate solution 0.001. Now we put back our bridge and the electrode, and now of course the potential will change. Okay, and that is equal the slope we expect when we have one electron moving around. Good. So the theory you will discuss during the lecture or during the introduction of the experiment.